AMS is a high-energy physics experiment.
AMS is led by a Nobel laureate from MIT, Professor Samuel Tane.
And universe is an accelerator of particles.
One of the biggest advantages is the energies that can be achieved in space.
Strong piece of evidence that there are not large antimatter galaxies or stars.
Managed to gather a collaboration of over 60 different institutes from 16 different countries around the world.
And we need to understand what is the nature of this dark matter.
You know, that there were supposed to be equal amounts of matter and antimatter when it all started.
AMS is a high-energy physics experiment using similar detectors to what the high-energy physicists use in their ground-based experiments.
And universe is an accelerator of particles. In the universe, in all these explosions of stars, etc., particles are produced, they are accelerated, and that's what we see at the end. From these particles accelerated, we try to understand the phenomenon at the source.
One of the biggest advantages is the energies that can be achieved in space. There is no collider. Even if it was a superconducting super collider that was canceled in the 90s, there is nothing that can achieve the energies in space by several orders of magnitude.
We expect to see about 25,000 particles per second coming through AMS. Now, the majority of those we throw out because it didn't go through all the detectors, or for some other reason it doesn't look like a very interesting particle. So as a particle comes through, each one of the detectors will measure that particle, and the detectors measure different things about the particle. They may measure the mass, the momentum, the speed, the electrical charge of the particle. And sometimes we measure those in multiple ways, so that we may have a measurement of the particle in one detector that tells us its mass, and then we have a measurement in another detector that tells us its mass, so we can verify the two.
We are looking for is anti-nuclei, I mean anti-helium or anti-carbon, because this kind of nuclei, anti-nuclei, can only be produced in anti-stars.
You know, that there were supposed to be equal amounts of matter and antimatter when it all started. We know where the matter is, you know, we're made of it, but what happened to all the antimatter?
At the core is the magnet. Without the magnet, we would not be able to tell the charge of the particle, because the particle, as it comes through the detectors, is bent in a magnetic field, and we can measure the trajectory of that particle, and as we measure the trajectory, we can tell exactly which way it was going, so that tells us what the charge was. By measuring the mass and the charge and the energy, we then know this was a helium atom, or this was an anti-helium atom.
So the particle goes through the magnet. It's bent in one direction or the other direction, depending on the sign of the particle. And then it crosses all the other detectors. During this travel through the magnet, the particle has seen two layers of what we call scintillators. When the particles go through, some light is produced, we get an electric signal. And this tells us, because we measure very precisely the time between the two detectors, a picosecond, 100 picoseconds resolution, which is extremely precise.
This detector is made of 8 of them in one direction and other 8 of them in the other direction. These are the detectors that provide the signal, so we can measure the time of flight that we are talking before. The way it works is that if a particle traverses this detector like that, light is produced inside, and it propagates at the two sides where we have photomultiplier that detect the light and can measure the time of arrival of this particle.
The TRD, or transition radiation detector, is the detector at the very top of the experiment stack, and what it's used for is to differentiate heavy particles from light particles. So electrons and positrons, which are light, and then protons and neutrons, which are heavy. It does this by using a series of straw tubes filled with a mixture of xenon and carbon dioxide gas. And as particles come through, the lighter ones will give off what they call transition radiation, which can then be detected in the gas tubes.
The time of flight system. The time of flight is actually above and below the main tracker. The tracker is used to track the particles as they fly through the bore of the magnet system. And the time of flight system is used to actually measure the speed of the particle. And it's used as a trigger to tell all the other detectors, okay, look for this particle.
There is a mysterious part of the universe which is 90% of the mass of the universe, but not visible. We call it dark matter. And we need to understand what is the nature of this dark matter. And for that research, the ECAL is really a key detector.
The ECAL is the detector at the very bottom of the experiment, and it's basically a sheet of lead embedded with fiber optics, and it's intended to actually stop particles completely and break them up into various components and measure the total energy of the particle.
We basically have put every type of instrument that a high energy physicist would like to have onto AMS. It has pretty much everything anyone would ever ask for.
You need that somewhere in the universe there is a star made of antimatter, and that's what we are looking for. Anti-helium, anti-carbon, and AMS is so precise that you can detect one nuclei among 1 billion nuclei of matter.
The current version of AMS has roughly 330,000 channels. Most of them are in the heart of the experiment, which is called the tracker. That generates the most data. But all the other detectors generate data as well that help confirm and measure the properties of the particles in different ways.
In the 3 years that was our original primary mission, we will gather 7 terabytes of data on the ground, of useful data. Which is a ridiculously large number.
In order to go from construction to analysis. And of course, next year we'll spend a lot of time first in Florida, then in Houston when the first data come back, because we all want to be there to see the first data, of course.
It'll be elation when it launches. It'll be a huge relief when we get it on station. That's going to be a huge milestone. We see that we've got the field on it. That's going to be fantastic. But then when we start getting data, and of course, I'm not going to know good data from bad data. I'm going to be turning to all these guys and saying, all right, are you getting what you're hoping to get?
Absolutely, the most fascinating one I've ever worked on. It's been the most culturally broadening experience and technically challenging and stimulating and exciting job I have ever worked on.
We are excited to see the result of 15 years work, which is a lot for everybody, but it's been nice to work in this project.
It will be a great relief to see it up there. We've worked a very long time on this, and we're very excited to see that we're getting towards the end here, and we're getting to the point where it will be up there collecting data and doing the science that it was designed to do. So it's a very exciting time for us.
It's been a long time in coming. We've had a few ups and downs along the way. But we built a good detector that should give us science, unprecedented science from the International Space Station, and just getting it up there and operational will be a huge sigh of relief. Will bring a huge sigh of relief to me, and I'm sure to my team, who have been diligently working on this for at least 10 years, most of them.
But then what they really find is something completely different, unexpected, and often much more interesting and much more useful discovery than what they originally went out to find.
So, it has been true for each accelerator, in each country, each experiment, always surprises. So now we are almost sure that the main discovery of AMS is something we have not at all thought about.